Welcome back to Week 9 of our course Introduction to Physics and Biophysics. In the previous week, we studied waves and sound, learning how vibrations in matter can transmit energy and carry information, from the sound we hear to the ultrasound images used in medical diagnosis. We are moving from sound waves to light, a critical form of electromagnetic radiation. Light and optics are everywhere in healthcare, fundamental to corrective lenses, microscopes, endoscopes, fiber optics, and laser surgery. By the end of this lesson, we will connect the basic laws of reflection and refraction to medical imaging and vision correction. Light is a form of electromagnetic wave. It consists of varying electric and magnetic fields that oscillate perpendicular to each other and the wave's direction of propagation. Light does not require a medium. It can travel through a vacuum at the speed c, which is a universal physical constant with an exact value of 299,792,458 meters per second. Physicists use two complementary models: the wave model, useful for phenomena like reflection, refraction, interference, and diffraction, and the particle model, useful for explaining quantum effects like the photoelectric effect. If we want to understand how a patient's corrective lenses work, which model of light should we use? We should use the wave model, as it is appropriate for understanding the bending of light. Since lenses function by causing the refraction of light, the wave model provides the necessary framework to analyze how they correct vision. Reflection occurs when light encounters an object and bounces off a surface, staying within the original medium. The governing principle is the law of reflection. The angle of incidence equals the angle of reflection. This law holds true for both flat mirrors, which create virtual, upright images, and curved mirrors, such as those in ophthalmoscopes. The principle of reciprocity states that if you can see a light source via a mirror, the source can see you from where the light originated. Why is this reciprocal path assured by the laws of optics? The reciprocal path is assured because the law of reflection dictates that the angle of incidence equals the angle of reflection. The path light takes from point A to point B is exactly the same as the path it takes from point B to point A. Thus, if the light ray reaches your eye from the mirror, the same path is possible in reverse. Refraction is the bending of light as it passes from one medium to another, such as from air into the cornea of the eye. This occurs because the speed of light changes as it moves through different materials. This change in speed is quantified by the refractive index, defined as the ratio of the speed of light in a vacuum to the speed of light in the material. N equals c over v. The index of refraction is always greater than or equal to 1. The exact bending is calculated using Snell's law. A ray of light moves from the air into the dense medium of a mineral sample. Does the light ray speed up or slow down, and does it bend toward or away from the perpendicular line? When light enters a material denser than air, it slows down because the speed of light in matter is less than the speed of light in a vacuum. As the light slows down, its direction changes, and the ray moves closer to the perpendicular. Conversely, if the ray speeds up, it moves away from the perpendicular. Lenses are optical devices that rely entirely on refraction to form images. They are categorized based on whether they converge or diverge light rays. Convex lenses are converging, while concave lenses are diverging. The human eye acts as a natural optical instrument. The cornea and the crystalline lens function together like a compound lens, ensuring incoming light rays are refracted to focus an image precisely onto the retina. The cornea provides about 2/3 of the total focusing power, and the lens provides the remaining adjustable power known as accommodation. A patient presents with nearsightedness. How is their vision defect physically described, and what type of corrective lens is used to fix it? In myopia, light focuses in front of the retina, making distant objects appear blurry. To correct this, an eye doctor prescribes a concave lens. This diverging lens spreads the light rays slightly before they enter the eye, pushing the focal point backward so that the image is formed precisely on the retina, enabling clear vision. Optical principles are foundational to medical tools. Instruments like the microscope use convex lenses to produce a highly magnified image. The ophthalmoscope uses reflection and refraction to examine the retina. A major category of medical device, the endoscope, relies on total internal reflection. Endoscopes rely on fiber optics to transmit images through flexible tubes. Explain the principle of total internal reflection and why it is critical for guiding light inside a fiber optic cable. Total internal reflection occurs when light attempts to move from a higher refractive index medium into a lower refractive index medium. If the angle at which the light ray strikes the boundary is greater than the critical angle, refraction cannot occur, and all of the light must be reflected. This means the light is continually reflected internally along the fiber, allowing it to be guided along the cable, even if it is bent. This principle allows endoscopes to transmit light into the body and carry images back to a screen for minimally invasive diagnosis. Laser therapy also relies on light amplified by stimulated emission to produce an intense beam used in eye surgery and tissue repair. Light itself is essential for general health, regulating the circadian rhythm and used in phototherapy to treat newborn jaundice. We have covered the fundamental behaviors of light and their direct application in health sciences. Light's nature as an electromagnetic wave, exhibiting wave-particle duality, is used in both classical optics and quantum effects. Reflection, where light bounces off a surface, is crucial for ophthalmoscopes and dental mirrors. Refraction, the bending of light due to speed change, is vital for cornea, lens focusing, and vision correction. Lenses, whether converging or diverging, are fundamental to eyeglasses and microscopes. And total internal reflection, or TIR, is key for light guidance in endoscopes and data transmission. Understanding these concepts is crucial because optics provides the tools and techniques that allow us to see, diagnose, and treat conditions throughout the human body. Next week, we will shift from light energy to another vital physical phenomenon that runs through every living being, electricity. Thank you for joining this week's session. See you in week 10, Electricity and Circuits.